V, then we show that it has an orthonormal basis. And if it is an inner product space, then it has any basis, U1, U2 up to UN. And so to show that it has an orthonormal basis, it is enough to show that it has an orthogonal basis, since every orthogonal basis can be normalized to produce an orthogonal basis. Now, the following process will produce an orthogonal basis. The first step, we pick the first element of the orthogonal basis we let the first element of the orthogonal basis be the first element of the basis we are looking at. Okay, the first element of the orthogonal basis is the first element of the basis we are looking at. So V1 is U1. Now, to obtain the second element of the orthogonal basis V2, which if it is the element of the orthogonal basis, then V2 should be orthogonal to V1. So we obtain it by computing the component of U2 that is orthogonal to the space W1, which is spanned by the vector V1. So how do we do that? V2 is going to be U, then minus that component. We get U2. To get V2, we get U2 minus the component, which is orthogonal, which minus the component which is orthogonal to the space W1 spanned by V1. So that one becomes our U2, and we know that is given by that. So we are saying that V2 is non-zero. If it is non-zero, then it ceases to be our element of interest, but it is non-zero because it is computed from U2 and U2 is computed from V1, and V1 is computed from U1, and U1 and U2 are basis vectors, meaning that they are linearly independent. Step 3 is to get the third element of the orthogonal basis. So that third element should be orthogonal to the first two, and to compute that, we find a component of U3, which is orthogonal to the space W. So that one is going to be V3 minus that. Gilbert, any problem? Did I see your hand raised? Any problem? I'm seeing your name appearing on my screen, Shava Gilbert. What is the problem? Or you are getting out? He's not even here. Okay. I think he's trying to enter, maybe, okay? So this is how we get the component U3 by doing that. And we know that the projection U3, it is the projection of U3. It is the component of U3 that is orthogonal to the subspace W2, which is spanned by V1 and V2. So that means that component is got by this formula, and means V3 is going to be given by that. It is going to be given by that, and continuing the process, we get even Vn. To get Vn, we compute the component of Un that is orthogonal to the space Wn, which is spanned by V1, V2, up to Vn minus 1. Up to Vn minus 1. And so that process is what we call the Gram-Schmit orthogonalization process. Okay. In the example, we have our inner product space V, which is a space of polynomials of degree less or equal to 3. And the inner product defined on that space is the integral from -1. When the inner product of two elements, two polynomials, f and g, is the integral from -1 up to 1 of f of t times g of t dt. Now, the question wants us to apply the Gram-Schmit orthogonalization process for this. So that means we want to find this orthogonal process. We want to find this orthogonal basis F0, F1, F2, F3 for V. And to do that, we start with any basis for V, and any basis for V, we can pick the standard basis for polynomials of degree less or equal to 3, which is S. So we want to use S to construct an orthogonal basis. So we perform the Blanchard orthogonalization to change it into orthogonal basis. So the proof tells us that we let the first element of the orthogonal basis be the first element of the standard basis. So F naught is 1. To find F2, we compute the component of T that is orthogonal to the space W1 spanned by F naught. So that one gives us T, then minus the component of T that is orthogonal to W1, the space spanned by F naught is inner product T, 1, then 1, 1, and that. So this is the only thing we are looking at because we only have F naught now. So when we take the inner product of T1, it gives us a 0. So we get F1 and as T. To get the second basis element in the orthogonal basis, we first compute the component of the component of T squared that is orthogonal to the space W2, which is spanned by F1 and F naught. So that is T2 minus C. That space is T2 inner product 1 times 1 plus C. This is for F naught. Then for F1, we have T squared T over T times T. So it is T minus this one gives us this one here. We saw it gives us when you do this, we get 2 over 3, then times 1, and this one gives us a 0. So we get F2 as that. So the last step is to get F3. The last step is to get F3, and to get F3, we get it from T3 minus the component of T3 that is orthogonal to the space W3 spanned by F2, F1, and F naught. So that is T3. This is the space spanned by F naught. It is T3, 1 over that times 1. Space spanned by F1, it is T. This is going to be T. This is supposed to be T cubed. Sorry, this T is cubed. It is T cubed, T, then TT. Then the space spanned by F2. F2, we got it as T squared minus a third. So it is T cubed. Then this inner product, this, then times the F2, which is that. And this one here gives us a 0 because it will be integral T cubed, which is T to the power 4 over 4. It gives us a 0 times 1. This one is integral. Yeah, this is the T to the power 4. This will be the integral T to the power 4 because I said this guy here is supposed to be a cube because this is T cubed. So integral T to the power 4, integral T to the power 4 becomes, and we compute both this and that. Of course, when we compute this, once this is 0, then we don't mind about what we get here. So this is integral T to the power 4, which is T to the power 5 over 5, and that one gives us the 2 over 5. Then when we integrate here, this is the integral T, it is integral T squared, which is T. I think this gives us negative 2 over 5. Then this one here gives us the 2 over 3. So we get this, then we multiply by this T. When we compute this is the integral. We compute it and then integrate. We get the T cubed minus 3 over 5. Okay. This is for that. And this one here is the T to the power 4, then T cubed which I think, okay, it also gives us a 0, t cubed, t cubed. This is t cubed times t, which is t to the power 4, so it is t to the power 5, so it also gives us a 0. Then this is from this one, and so when we divide this, we get the 3 over 5, so we get this as f as f3. So it means that the f naught, f1, f2, f3 is given by f naught, f1, f2, then f3. So this is an orthogonal basis for P3, for the vector space P3. Now, part of your exercise, I don't know, it is not appearing. Okay, I can work on this part of the exercise but the part of the exercise, your exercise is to, what you can work out is to find an orthonormal basis. What do? You normalize each of these vectors. You normalize each of these vectors. Let me see if I can bring this slide a bit clearer. As people think of the questions, people should be thinking of the questions. People should be thinking of the questions as I work on that, as I work on the exercise. People should be thinking of questions as I work on the exercise. As I work on the exercise here. I am working on the exercise. This is teacher. Okay, questions? Members, questions? Questions. Okay, so this is the exercise I was talking about. Yeah, this is the exercise. This is the